Okay, good morning everyone. Let's get started. We have a lot to do today. So this is Introduction to Computational Complexity number 2. Okay, so before we start though, let me maybe say a few things about this week. So you will not get a homework today because there's a midterm on Wednesday. So in some sense, like a little break. So that's good. But we will give like some practice problems, maybe tomorrow or something like that, so that you can practice for the midterm. But really, like the best way, if you ask what's the best way to prepare for the midterm, well, it's as we said, like if you're doing the homework, you've been like preparing for the midterm as well anyway. But like, yeah, make sure like you go over those practice problems as well. Make sure you go over the slides. And make sure you understand everything there. And if you do that, I think all should be good. And also, another note is that, so we have, Ryan and I have office hours on Tuesdays and Thursdays. And Tuesday office hours are great, like we got a bunch of people come in. But Thursday office hours, you usually get a bit lonely. Okay, so I just want to encourage you to make use of today's office hours as well. I think like it's a great time to, come in and ask questions about the lectures that we've done that week, this week. Get clarifications. We can go over things if you didn't understand it, whatever. Like or we can just chat. But like this is time that we reserve for you guys, so make use of it. Okay, so let's start this lecture, and the way we're going to start this lecture is going to be by talking about two heroes. The first hero is Kurt Gödel, who lived from 1906 to 1978, and we've already talked about him a little bit. He was a logician, mathematician, philosopher. He made great contributions to mathematical logic, considered to be one of the most important logicians in history, right? Especially to foundation of mathematics. We talked about the completeness theorem. We're going to also talk about the incompleteness theorems of Gödel. So he was quite amazing person. And then another amazing person is John von Neumann, who lived from 1903 to 1957. So both of them lived around the time Alan Turing lived. And if you go to like the Wikipedia page for John von Neumann, so there's like a table of contents, right? So if you look at like his career and abilities, okay, this is the list you get. Set theory, geometry, measure theory, ergodic theory, operator theory, list goes on and on and on. Some of the highlights, I would say, is like he gave a mathematical formulation of quantum mechanics. He founded the field of game theory in mathematics. And he created some of the first general purpose computers. So you can also think of him as one of the fathers of computer science as well. So he was, again, an amazing person. And what I want to talk about now, briefly, is a letter that Gödel wrote to von Neumann. So they were close friends. And in 1956, Gödel wrote a letter to von Neumann. I'm not going to go over the whole letter, but here's a nice part of the letter. Okay? All right, so let's look at what this says. Okay? So Gödel says, one can obviously easily construct a Turing machine which for every formula f in first order predicate logic and every natural number n allows one to decide if there's a proof of f of length n. Okay, length being the number of symbols. So what he's saying here is, he's saying, look, John, look at this following computational problem. So the input is a first order logic formula f and a number m. And the output is supposed to be yes if there's a proof of f of length m and no otherwise. And he says, obviously this is decidable. You can do this using, for example, brute force search. Okay. And then he says, introduces some notation. Let psi f comma m be the number of steps the machine requires for this. And let phi of m be the maximum over all of f of psi f comma n. And the question is how fast phi of n grows for an optimal machine. Okay, so he's introducing this notation psi f comma m, which is the number of steps required for the input f comma m. And then he's saying phi of m is the maximum over all f of psi. So this is like a worst case notion of running time he's introducing here. Now, in some sense, phi of m, you can think of it as like the running time in some of the machine that would solve this problem. Okay? Because really f, you can say, well, the formulas we would be interested in, well, maybe they have like some constant length, so that doesn't really specify the problem length. So m really specifies the problem length. So you can say phi of m is like t of n, where t is the running time. And question is, how fast does phi of m grow for an optimal machine? So in some sense, he's asking like the intrinsic complexity of this decision problem. Okay, so it's amazing. So this is like before the time like computational complexity was born. Okay, and then he says one can show that phi of n is at least k times n. And he says if there really were a machine with phi of n proportional to k times n, or even kn squared, this would have consequences of the greatest importance. Okay, so he's making a claim. He's saying phi of m is at least k of m, k times m. So he's saying he's proving a lower bound. He claims that he has a lower bound. I don't think this is trivial, but he claims that he knows this. And then he says, you know what? If like this was like the true growth rate of phi of m, k times m or km squared, which really means, if you could really beat brute force search, okay, then quoting him, this would have consequences of the greatest importance. So why is that? And then he goes on to explain what he means by that. He says, well, namely, it would obviously mean that in spite of the undecidability of the Entscheidungsproblem, the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. Okay? After all, one would simply have to choose a natural number n so large that when the machine does not deliver a result, it makes no sense to think more about the problem. So you could imagine, setting n to 1 billion, and you say, well, you ask the machine, is there a proof of length at most 1 billion? And if the machine says no, well, you say, well, if there's no proof of length at most 1 billion, maybe I shouldn't bother trying to prove it myself. Okay? And if it says, yes, there is a proof, well, then you know the answer to the question that you wanted. And then he says, and he's an optimistic guy, he says, now it seems to me, however, to be completely within the realm of possibility that phi n grows that slowly. Okay, so this is quite an amazing letter. As I said, this is like about the time that computer science was being born, but like really computational complexity was not like a field that was born yet. But you could really take this letter and create the field of computational complexity theory from this letter. So yeah, that's quite an interesting letter that was discovered. I guess after they were dead. Okay, so today, what are we going to do today? Today we're going to talk about both the power of computation by looking at some really amazing algorithms that do surprising things. And then we're also going to talk about the limits of computation by showing you that there are problems that require at least, let's say, whatever time bound you give me, n squared, n cubed, 2 to the n, there are problems that require that many steps. So it's not like you can solve everything in polynomial time. Okay? So we're going to look at both of these things. But to look at some of the algorithms, to analyze some of the algorithms that we're going to look at today, we have to do some running time analysis. And when you do running time analysis, well, if your algorithm is like an iterative algorithm, then probably you're going to end up with some summation that you will have to analyze, the big O of. Or it might be a recursive algorithm, and then you have some recursive relation for the running time, and you will have to deal with the recursive running time. Okay, so let me now, like, very briefly go over some techniques to deal with these two things. I think you might find them useful in your life. So first, dealing with summations. There are various techniques you can use. Let me give you like 5 common techniques that are used. So you can first of all use rough bounding. So rough bounding works like this. Here's an example. So let's say you have like the sum of I equals 1 to n, so 1 plus 2 plus 3 all the way up to n. Now maybe you don't know the exact formula for this. Maybe it's a more complicated thing. But you can say, well, you know what? This is like at most n plus n plus n plus n, n times. So clearly this is like at most n squares, and that tells you this is big O of n squared. Now once you've done that, you should also be careful about whether this is tight or not. So it may not be a tight upper bound. So you should also think about maybe lower bounding this, and you can say, well, okay, this sum from 1 to n, let me get rid of the first half, the lowest n over 2 terms, and just look at the largest n over 2 terms. So I goes from n over 2 to n. So clearly these numbers are all at least n over 2. The smallest one is n over 2. There are n over 2 of them. So that is basically n squared over 4 at least. And that shows you it's omega n squared. So it's big O n squared. It's omega, big omega n squared. So it's theta n squared. So, you know, just doing like rough bounding like this can get you to the right asymptotic bound. You can, of course, do exact computation. You can say, well, the sum of the i's are, I know, n times n plus 1 over 2, which is n squared plus 2 over n plus 1 over 2. The lower order terms and the constant terms don't matter, so that's theta n squared. Another useful summation formula that you should know is I equals 0 to n, x to the I. This is equal to x to the n plus 1 minus 1 divided by x minus 1. If the absolute value of x is less than 1, and you let n go to infinity, okay, you see that this term x to the n plus 1 basically disappears. And you're left with minus 1 over x minus 1, which is same as 1 over 1 minus x. And you can say, okay, let's take this, let's differentiate it. Maybe something interesting happens. You differentiate it and you say I times x to I minus 1 is 1 over 1 minus x squared. So that's a neat trick of differentiating inequalities like this. Actually, if you multiply this now by x, probably this would be something you would see more often, I times x to the I. And you can actually differentiate this one more time and see what you get. I won't do it, but like that's also interesting. You can do induction to deal with summation. So maybe you have a summation like this, I equals 0 to n, 3 to the I. And you say, okay, 3 to the I, you know, like that kind of function, is an exponential function, is a super fast growing function. So you might guess that the last term in this summation, 3 to the n, is the dominating term. So you might guess that, well, maybe this is big O of 3 to the n. Okay? Now that's only a guess, right? But then you can actually say, okay, I'm going to try to prove this. And you can prove it by induction. Now one thing you should be careful about here is you should specify the constant c. So don't prove this by induction by saying the sum of 3 to the I is big O of 3 to the n. And then use that notation to do your induction. Because it's important that when you're doing your induction that the constant c does not change value. And if you write it as big O of 3 to the n in your argument, implicitly that constant might change and you may not realize it. And you might get a wrong proof. Okay? So write down c explicitly and do your induction. Telescoping series are interesting. So if you have some sum like this, 1 over I times I plus 1, you can see that you can write it as the sum 1 over I minus 1 over I plus 1. Okay, so there's no magic going on here. If you subtract 1 over I from 1 over I plus 1, that's exactly what you get. And you write this down, you see it's something like this. And these terms, 1 over 2, minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3, they cancel each other out. And you get 1 minus 1 over n plus 1. So that's a really nice trick. And lastly, comparison with an integral is also a really cool trick. So the idea here is that if you have like a sum I equals 1 to n of f of I, this is roughly going to be equal to the integral of f of x dx, where x goes from 1 to n. So here's an example. Let's say you have the sum 1 over I. Okay? So that's going to be roughly equal to the integral of 1 over x. So why is that? Okay, so let's look at the graph. And by the way, this is the natural logarithm of n. So if you look at the graph, okay, so these orange rectangles are basically the elements in the sum 1 over I. So this is 1 over 1, represents 1 over 1. The area of this rectangle is 1, and that represents 1 over 1. The area of this rectangle is 1 over 2, and that represents the second element. This is 1 over 3, that represents the third element, and so on. So the area of the orange rectangles is the sum, okay, 1 over I. Now you look at the function 1 over x. It goes like this. It touches these rectangles at the corner, right corner here. Okay. And then you say, okay, if I look at the integral from 1 to n, right, that's the area under the curve from this point to that point. Well, definitely, if I take that area and add 1 to it, add the area of this rectangle, that will be an upper bound on the area of all the orange rectangles. Okay, and similarly you can say for a lower bound, let's look at the function 1 over x plus 1. Okay, and that's this function there. It touches the rectangles on the left corners now, and the area under this curve is obviously a lower bound on the area of the rectangles. Okay, so this is a really neat, nice trick. So you should keep it in your toolbox. Okay, so that's dealing with summations. Now let's see how we can deal with recursion. Okay, and I'm gonna show this by an example that I hope that you've all seen before, which is merge sort. Okay, so sorting a given list and array of list of elements with merge sort, there are 3 steps, as you know. You recursively sort the right half, you recursively sort the left half, and then you merge combine the 2 sorted lists. Now, when here, first of all, a remark, the input size, the length of the input, we're going to consider it to be the length of the list, the length of the array, which is going to be n. Okay? Why? Because we're assuming we're in the RAM model. We're assuming that, let's say, if this is a list of integers, the integers are at most 64 bits long. So if they're all 64 bits, the length of the input would be 64 times n. But, n, 64, n, same thing for us, right? So doesn't matter. We're just going to say it's easier to just consider the length as the size of the list. And then you say, OK, T of n, the running time of this algorithm, what's the recursive relation? It's upper bounded by, who would like to volunteer? Yes?
2 times n over 2 ceiling plus order of n.
2 times T of n over 2, basically, plus order of n. OK, let's say I'm assuming n is even. OK, and then you write this recursive relationship. Now you have to solve it. Well, what does it mean? Now, what kind of function T of n actually satisfies this recursive relationship? To solve this, first of all, note that if you look at the number of steps that this algorithm takes, but you don't count the work done by the recursive calls, it's like order n, right? So you make a recursive function call in the first step. That's one step, okay? Because I'm not counting the work done by that recursive call. In the second step, I'm just making one step. I'm just making a function call. And I'm not counting the work done by that recursive function call. And then in the third step, I'm doing order n steps. So because merging two sorted lists takes big O of n. So if I don't count the work done by the recursive calls, then it's at one level I'm doing order n. OK, so to solve these kinds of recursive functions, recursive structures, our recommendation is to use a recursion tree. OK, so here's the recursion tree for this. So at the top, at the root, we have n elements to sort. Then we divide into two parts, n over 2, n over 2, and recursively solve each of them. So n over 2 gets divided into n over 4, and so on. And then also what we're going to do is we're going to label each node by the work that is being done for that node. So as I said, at the top level, at the root, right, the amount of work you're doing is order big O of n. So it's C times n. But I'm writing n here, just not C times n, for simplicity. OK? So at the top level, I'm doing big O of n work. I'm not counting the work being done by the recursive calls, because I'm going to count it in the subnodes, in the nodes going down. And then you say, OK, at each node, if it's like of certain size, the amount of work you do is proportional to the size of that node. And then you say, OK, first, what is the number of distinct problems at level j, distinct nodes at level j? OK, so the levels go from 0, 1, 2, and so on. How many nodes do I have at level j? Yeah. You have 2 to the j, exactly. OK, hope everyone sees that. And then how many operations do you do per node at level j? Right, so I'm asking for the red value, basically. What's that?
N over 2 to the j?
N over 2 to the j, yes. But there's also some constant, C times n over 2 to the j. So that means that if I look at a particular level and sum up all the work I'm doing at one level, it's going to be C times n, because it's 2 to the j times C times n over 2 to the j. The 2 to the j's cancel out, so it's C times n per level. So I could write like number of operations per level here, and at each level I see it's C times n. C times n. And then to finish this off, you say, OK, how many levels do I have? Log base 2 of n. I guess the level number of the last level is log base 2 of n. And then you say the total cost is going to be n log n. Yeah.
And for our actual analysis, can we gloss over some of the details? Because strictly speaking, merge sort is T of n over 2 ceiling as T of n over 2 floor, and there's nothing actually stopping you from saying that, well, there's nothing that you can actually prove to say that this is actually a monotonically increasing function. So for all you know, it could spike down. So can we just gloss over the details and say that we don't care about ceilings and floors?
The ceilings and floors wouldn't affect the running time.
You don't actually know that, because for all you know, you could have a really bad function that goes straight up and then straight down for some particular value and straight up again.
Okay, so let's discuss this after class, okay? But it's yeah, let's see if that would make a difference. But okay. And then let me just mention quickly that there's actually a theorem called the master theorem that gives you a formula basically for T of n for recurrence relations like this. Okay, so it says, you know, base case is T of n is at most some constant c. And the recursive relation is, let's say, T of n is at most a times T of n divided by b plus big O of n to the d. So here, a is like the number of recursive calls that you're making. B is like the input size or the shrinkage factor. Input size shrinkage factor, and d is the exponent of the combined step. So order n to the d is like, you can think of it as like combined step. And you can see like this formula gives like if a is equal to b to the d, it's n to the d log n. If a is less than b to the d, it's n order n to the d. If a is more than b to the d, then it's n to the log base b of a. And you know, if you say like, how do you prove this? Well, you sort of do it with the recursion tree. Okay, so I actually don't recommend you to like memorize the master theorem at all. So whenever you get a recurrence relation, well, just figure it out yourself. Build the recursion tree and do the computation and figure it out yourself. So you don't have to really know this theorem, but it exists and you should know the existence of it. Yeah.
Well, isn't there a tighter bound for the log base b of a equals d case for this n to the d of log to the d power n in the real version?
And I'm not sure. I'm not sure. There might, I mean, they changed the master theorem? Okay. I mean, anyway, like we can discuss these after class. Okay, so so that's the formula, but as I said, you don't really need to know it. Okay, so now let's go on to the main part that I want to discuss today: the power of computation and algorithms. Okay, so here what I want to show you is that the space of efficient algorithms, the space of algorithms is really, really rich. And algorithms can really do interesting and clever things. Okay? So the first example we're going to look at is integer multiplication, which is something we discussed briefly last time. So here we are given two n-digit numbers x and y, and we want the product of x and y. And we saw like a terrible algorithm last time where you like add x to itself y times, and like we saw that that's really an exponential time algorithm. And I also mentioned that this algorithm that you've learned in grade school of multiplying numbers is like a pretty decent algorithm. Okay, so if you look at this, if you want to look at the running time, so what do? So you take 4, you multiply it by 8, you multiply 4 by 7, 4 by 6, 4 by 5, you keep track of the carries and everything, but that basically, that step, this like getting to this 22712 is like big O of n operations. And of course, all the rows take big O of n operations. There are n rows in total, so that's like order big O of n squared. Right here, technically, I guess like the input length is 2n, but that's not an important issue. Okay, so you might think, probably this is the best you can do. Like, what else can you do, right? I mean, but a good algorithm designer thinks, how can we do better? Okay, so let's try a different approach and see what happens. So this is x, this is y, and what we're going to do is we're going to divide both of them up into two parts. So I'm going to divide x up into two equal length parts, a and b. So a is 5, 6, b is 7, 8. Similarly for y. Y is 1, 2, 3, 4. So 1, 2 is the c part, 3, 4 is the d part. And then if you do this, you can see that x really is equal to 10 to the n over 2 times a plus b, right? So you're saying take a, add 2 zeros to it, right? Shift it by 2, and then add b to that number. Okay, so multiplying by 10 to the n over 2 is just adding zeros to the right side of a. And similarly, y is like 10 to the n over 2 times c plus d. Actually, since we're computer scientists, let's go to the binary representation of numbers. So x is a binary number, y is a binary number, and we want to multiply these binary numbers. And well, the same relationship holds. Now x is equal to 2 to the n over 2 times a plus b, and y is equal to 2 to the n over 2 times c plus d. Okay, then let's look at what x times y is in this way of writing things. Well, that's the product of these two things. Expanded out, so we get 2 to the n times ac plus 2 to the n over 2 times ad plus bc, and then plus bd. Okay, so then what do you think? What should we try to do? Anyone? Yes.
So we can do a bit of manipulation to change it to free multiplication operations and summation operations, and then
free multiplication?
Yeah, for a, b, c, d. So no, we can.
You were saying free of well.
Free of them.
3.
Yeah. And then
how do you do 3? So
So
do you know this?
Yeah.
Okay, so I want to know from someone who has not seen this before. Yes.
How much would you recursively call all the multiplication of
Right. Excellent. Right. I mean, this suggests, this screams at you recursion. Hopefully, okay, it should. Like you have a times c, a times d, b times c, b times d. These are all multiplications that you're doing on smaller instances of size n over 2 each, right? So you have to try recursion here. Okay, so say, okay, let's try recursion. Okay, recursively compute AC, AD, BC, and BD, and then do the additions. Okay, and the base case was going to be one-digit numbers, which we know how to do trivially. What is the running time, the recursive relation for T of n? T of n is at most, well, I have 4 recursive calls. They're each on size n over 2 bits. So that's 4 times n over 2. Okay, and then to do these additions. So the multiplication by 2 to the n and 2 to the n over 2 is just adding zeros to the end of these things. And doing the additions, they take big O of n time. Now you say, okay, well, what kind of running time is this? Okay, so to do that, you go to your recursive tree. This is how it looks like. And we do our analysis as before. We say first, what is the number of distinct problems at level j? 4 to the j. What is the number of operations per node at level j?
1 over 2 to the j.
N over 2 to the j. And we have a constant, c times n over 2 to the j. Okay? So in total per level, we're doing c times n times 2 to the j. Okay, we multiply these out. All right, so that's the number of operations per level. Number of levels is log base 2 of n. So the total cost, I guess it's log base 4. No, I'm going n over 2. Log base 2 of n, so that's right. Now you say, okay, the total cost is what? J equals 0 to log base 2 of n, c times n times 2 to the j. So what is that? Well, first of all, let's take out c times n. It does not depend on j. Okay. Now we have j from 0 to log base 2 of n of 2 to the j. Now you can use your formula, exact formula here, but as I mentioned before, you have this exponential. It's dominated by the last term. So really, this summation will be 2 to the log base 2 of n. Big O of 2 to the log base 2 of n. Now what is 2 to the log base 2 of n? That's n. So what did you get? We had cn times n. So that's c times n squared, big O of n squared. So we did all that work, but we didn't improve the grade school algorithm. So that's kind of disappointing. But, you know, a good algorithm designer says, how can we do better? Okay. So let's come back to this, because this still seems like some non-trivial, we have some non-trivial ideas going on here. So maybe we can push it some more. And then, you know, if you look at this, and if you ask like Ryan, he would probably say, well, you know what? We don't really care about AD and BC here, per se, right? We only care about the sum, AD plus BC, right? So maybe we can get away with doing just 3 products, 3 multiplications, 3 recursive calls, rather than the 4. And he says, okay, take a look at this. A plus B times C plus D. You multiply that out, it's AC plus AD plus BC plus BD. And you see something interesting here. So this is AD plus BC. You say, okay, nice. So if I compute AC recursively, I compute BD recursively, and then I compute this product, well, if I then subtract from this product AC plus BD, then I will get AD plus BC. Nice. So that means using only 3 multiplications, I get to the quantities that I want to get to. Okay? So then T of n is at most 3 times T of n over 2 plus big O of n. Now, it's still not clear, is this better or not? Now, it could still be, I mean, we are definitely doing something better. This was 4 before, and now it's 3. But it's not clear if asymptotically we're doing better or not. Okay, so this might still end up being n squared. So we have to do the analysis, so we do it. Okay, so this is the tree now. We ask the same questions. Number of distinct problems at level j. That's 3 to the j. Number of operations per node at level j. That's going to be now, well, the same c times n over 2 to the j. So per level, we have cn 3 to the j over 2 to the j. So that's the number of operations per level. Number of levels is log base 2 of n. And then you say the total cost now is j equals 0 to log base 2 of n, c times n, 3 to the j over 2 to the j. You could also write this as 1.5 to the j if you wanted to. Okay, so let's look at this a little bit closely. Okay, so again, we're going to take out the c times n from the sum. And then we're going to do the same trick. We're going to say, well, this sum is going to be dominated by the last term. So when you plug in j equals log base 2 of n. So that's going to give us basically, well, I should say, yeah, it's not the same c, I guess. And I should put a less than or equal to sign here. But yeah, so it's less than or equal to some constant, not the same as this one. C times n, 3 to the log base 2 of n, divided by 2 to the power log base 2 of n. Now we know what this puppy is. 2 to the log base 2 of n is n. So that means the n's cancel out. So you have c times 3 log base 2 of n. Now by the properties of log, you can interchange the 3 and the n here. So this becomes c times n log base 2 of 3. Okay, and that means this is big O of n to the log base 2 of 3. And n to the, so log base 2 of 3, I believe, is about 1.58 or something like that. So we did it, right? So that's like much better than n squared. Okay, so this is called the Karatsuba algorithm for matrix multiplication. Now you might think probably this is the best, right? What can you do? But a good algorithm designer always asks, can we do better? Okay, and you know, you should be asking a very crucial question here, like why divide by 2? Like why divide x into 2 halves a and b? Well, let's divide into 3 parts, n over 3 each. Let's replace these 9 multiplications with only 5 multiplications. Okay, so then you do this kind of trick, you get this kind of recurrence relationship, and then T of n is order n to the log base 3 of 5. I think log base 3 of 5 is about 1.46, I think, if I remember correctly. So that's better, okay? I mean, the point is this is definitely better than the other one. And you can keep going, okay? So there's like, actually you can show that you can do it in big O of n to the 1 plus epsilon for any constant epsilon. And this is actually an interesting point I want to make, because last time I said, you know what, the intrinsic complexity of a problem is like the best algorithm that solves the problem. Well, maybe there is no best algorithm. There's always like maybe a better one, like here. So that's interesting, food for thought. And the best world record, as of now, I believe is n times log n times 2 to the big O of log star of n. And this is a relatively new result from 2007. Okay, so now another very fundamental problem, matrix multiplication. Okay, so this is a super duper important problem. It comes up everywhere. A lot of the algorithms out there actually have the running time in big O, the running time of matrix multiplication, because they use matrix multiplication in their algorithm, and that's the dominating operation. Okay, so this is like a very important problem. So input is 2n by n matrices x and y. You want the product of x and y. Let's assume the entries are objects that we can multiply and add in like one-time unit. And note that like the input size is order n squared, but you know that's okay. Like doesn't matter. Really, the problem size is described by n. It scales with n. And then, okay, you say, if I want to know the ij entry of z, how do I compute that? So this is by definition of matrix multiplication. Z of ij is, you take the ith row of x, and you take the jth column of y, and you take the dot product of those things. Okay, those two vectors. And dot product means like you just take this sum k equals 1 to n, xi comma k, y, k comma j. Okay, so I hope you all know how to do matrix multiplication. Okay, so here's like a simple 2 by 2 example. If it was 2 by 2 matrices, A, B, C, D times E, F, G, H, well, the first entry of Z would be AE plus BG, the second entry would be AF plus BH, and so on. Okay, so what is the running time of basically the naive algorithm? So you basically compute each entry of Z by doing this. Okay, so this is like order n, big O of n, right? But you have to do this for each entry of Z. It has n squared entries, n cubed. Okay, and you know, people thought, believed that this was the best you could do. What else can you do, right? Okay, so let's see what else we can do. So if you look at matrix multiplication, you have two matrices x and y. Let's divide them up into 4 parts each. Okay, so that A, B, C, D, these are submatrices of x, and E, F, G, H is submatrices of y. And it turns out that, you can check this, when you multiply x and y, well, the resulting matrix Z, you can express it as AE plus BG. So you're doing matrix multiplication, AE and BG, and then you're adding them up, and so on. Just like the 2 by 2 multiplication we did, but like it generalizes to submatrices. And then that screams at you what? Recursion. Okay, so algorithm 2 is recursively compute the 8 products and do the additions. But maybe not surprisingly, this doesn't really give you anything faster than the naive algorithm, theta n cubed. And by now you should know, well, you know, the thing you want to do is you want to ask yourself, can I do it with less than 8 products or less than 8 recursive calls? And someone actually did this. In 1969, Strassen said, you know what? You can do it with 7. And like that's very amazing actually. And like I have no idea how he came up with this, but here's how he did it. Okay, he said, look at these 7 products. Okay, then said, look, the first entry AE plus BG is just Q1 plus Q4 minus Q5 plus Q7, right? Obviously. So I said AF plus BH, obviously it's Q3 plus Q5 and so on. Like it's like, come on. Kind of reminds me like in the first assignment we had this like problem of how do you negate like 3 variables with like 2 NOT gates. It's like, I don't know, just try it out. Someone tells you it can be done, you just do it. And I think like this is the same. Someone tells you it can be done, like you just do it. Okay, I don't know who told him that this could be done. But he had like a strong conviction that like this is possible. And he did it. And like, okay, so T of n, this is the recursive relation. Still not clear if it beats like n cubed, but you do the recursive tree analysis. It's like n to the log base 2 of 7, which is n to the 2.81. And this was like, wow. At the time, like people were like floored by this result. Like no one was expecting anything better than n cubed. So this is, as I said, from 1969. And this really opened people's minds to the idea that, algorithms can be really smart and really do tricky things and non-obvious things. And there's an actually interesting story behind matrix multiplication. So as I said, this is Strasson's algorithm, 1969. Here's the guy. Actually, he also tackled the integer multiplication problem with his buddy Arnold Schoenhage. And they did it in time n times log n times log log n. And for a very long time, this is from 71, this was the best until the 2007 result that I showed you, which basically replaced this log log n with like order 2 to the O big O of log star of n. But like, yeah, I mean, it's not a major improvement, I guess. Anyway, so this was a interesting story of matrix multiplication because like people like just kept improving this one after the other. So since 1969, in 78, there was n to the 2.796 algorithm by Pan. In 79, by Pini, Capavani, Romani, Lotti, 2.78. In 81, Schoenhage, like the guy we just seen, Strasson's buddy, he was like, okay, he made like a major improvement. It's 2.522. And at this point, like people are wondering, well, can we get it below 2.5? That would be amazing. So, and then Romani ditched his friends. I can do better than that, he said. So I'm going to do it 2.517. And then a major breakthrough, okay? 2.5 was beaten, and to 2.496 by Coppersmith and Vinograd. And then like Strasson was like, I gotta get back in this game. And he's like, okay, 2.479. And this was improved by a lot by Coppersmith and Vinograd, 2.376. And this remained the best for a very long time. No improvements for 20 years. But then something very interesting happened recently. So in 2010, this guy, Andrew Stotters, in his PhD thesis, showed that it's n to 2.374. But like, he didn't even mention this in the abstract. This was like casually mentioned in page 81 of his PhD thesis. And no one knew, like other than him and his like PhD advisors. And he left the field, like he's doing like business or whatever. But like we learned about this result because in 2011, Virginia Williams, who was a CMU PhD 2008, showed that you can do it in 2.373. Okay? And this was like a big news. Like we've improved the matrix multiplication algorithm. Like everyone is talking about it. But then like this guy was like, well, I don't know how this got released, but like since this was a big news, some people who knew about this result said, well, this guy already did it in 2.374. And didn't even like bother to tell it to anyone really. So then there was like a big debate about, well, is this like really a huge result, like worth celebrating, or is this like a minor improvement? I don't know. So you can make up your own mind about it. But like this was an interesting thing that happened at that time. So enormous open problem. Is there an n-squared time algorithm for matrix multiplication? I mean, there's no way, right? So that 2.373 is the right exponent. I don't know, like I don't believe that. So there must be some like nice expression for like that time bound, I think. So n squared is pretty nice. So n squared, can you do it in n squared? And notice like you cannot do it really in n squared, better than n squared. Why? Because, well, z has n squared entries. So just to write them down, it takes n squared time. Okay. Crossing bridges. I don't know if I should skip this or not. Yeah, kind of short on time. So I'm going to skip this. Pam, pam, pam. Okay, so some other interesting problems. So the problem that Gödel wrote about is like the theorem proving problem. Given a mathematical statement and integer k, is there a proof in ZFC set theory with at most k symbols? Like very important problem, but we don't expect that there is like an efficient algorithm for this. Okay, so we think that the best algorithm is exponential time. Testing primality, given an integer k, is k a prime number or not, is a very fundamental important problem. Now, any problem involving prime numbers is very fundamental and important in mathematics and in computer science. Why? Because prime numbers are like the basic building blocks of numbers, right? So it's like the atoms of molecules. Like every number is built up using prime numbers, and every number has a unique prime factorization. Okay, so they are like the building blocks for numbers, so they're very fundamental and important. And this problem, testing primality, was a very interesting problem for a very long time, because this was the canonical example of a problem which we could solve very efficiently using a randomized algorithm, something we have not talked yet, but we will talk about it. But we had no idea how to do it efficiently using a deterministic algorithm. Okay? But then in like 2001 or around that time, a breakthrough, a efficient deterministic algorithm is found for testing primality. And this really strengthened the belief, our belief that, you know what, randomization doesn't really provide you extra computational power, in the sense that if you have a efficient randomized algorithm, then we can efficiently de-randomize it. Okay? We cannot prove this, but this is the general belief we have. And another very interesting problem is the factoring problem. Given an integer k, find its prime factors. Now let me again just stress that in both of these problems, right, we're looking at inputs, we're looking at numbers that have thousands, millions of digits, right? Okay, so that's the magnitude of the problems. So we want to factor problems, we want to factor integers that have thousands of digits. So given an integer k, find its prime factors. Again, a very important problem in computer science. This one we don't think, like theorem proving, we don't think that there is an efficient algorithm for this. And in fact, the security of our crypto systems, most of the crypto systems that we use today, rely on this belief, this assumption. In other words, if someone could factor integers efficiently, they could hack into all of the systems that we use. Not all, but like a lot. So that's an interesting problem. Satisfiability is something I think we're going to see. Given a Boolean formula, is it satisfiable or not? Okay, so this is also, we've seen this in second lecture, I think. And it's a very important fundamental problem. Again, we don't think there's an efficient solution for it. Sudoku. Okay? So now here's the thing. Like with Sudoku, the normal Sudoku you know is like a 9 by 9. Right? Now that Sudoku by itself, 9 by 9, is not a computational problem. Why not? Yeah, it's constant size, basically. Like a problem, a computational problem is an infinite collection of instances and solutions. If you just say, oh, I have 9 by 9 Sudoku, well, that's like just a constant number of possibilities for that. So that doesn't qualify as a computational problem. But you can easily extend Sudoku to arbitrary dimensions. And then it becomes a computational problem. And then you can ask, what is the best algorithm that solves Sudoku, with respect to the dimension n, as a measure of dimension n. And again, we think that this is actually a very hard problem, that there's no efficient solution for this. Now, it turns out that, and we're going to discuss this later, but it turns out that like these hard problems, like Sudoku, satisfiability, theorem proving, they're intimately related in some way. In what way? It turns out like if you could solve Sudoku, if you gave me an algorithm that solved Sudoku efficiently, then it turns out that I can actually solve satisfiability efficiently, and I can also do theorem proving efficiently, and many other problems. So you might ask, well, what's so special about Sudoku? Right? Well, there's nothing special about Sudoku, actually. Like, if you solve any one of these problems efficiently, you can solve all of them efficiently. So they have this very interesting connection between them, which we're going to talk about later. OK, so now let's talk about the class P. So we're going to now define our first complexity classes. Okay, so the first complexity class, d time of T of n, is going to be the set of all languages L that's decided by big O of T of n time algorithm. Okay, so this is a set of languages that can be solved in time big O of T of n. And P, the complexity class, the infamous complexity class P, is just the union of d time n to the k for k in the natural numbers. Okay, so P is the class of problems that can be solved in time or big O of n to the k for some constant k. And we can also define exp, which is the exponential time class. And this is d time 2 to the n to the k. And it's obviously true that P is a proper subset of exponential time. Okay. So complexity theorists like to define different complexity classes and then try to understand the relationship between them. And we're going to define other complexity classes later on. But we're starting off with these two classes for now, P and exp. Okay. Now let's discuss what is efficient in theory and in practice. So in practice, if you have an algorithm that takes big O of n time, that's awesome. That's like really awesome. Okay. So, usually it won't get better than that because you will have to read the whole input anyway. So these are blazingly fast. And then if you did like n log n, that's like great, super, super fast. That's also really good. If you go to like n squared in practice, it's kind of efficient. Like it's good, but like it's not great. If you go to n cubed, now like, I don't know, it's like barely efficient in practice. It's sort of like maybe a boundary. Like n to the 5, we wouldn't call it efficient in practice, actually. N to the 10, it's definitely not efficient. Definitely not, in practice. N to the 100, it's like, yeah. Okay, so that's like in practice. What about in theory? In theory, we like to keep things simple. So I say, if it's in P, it's efficient. If it's not in P, it's not efficient. Okay, so that's our definition in some sense. So you, of course, like when you say this, like, oh, you're saying n to the 100 is efficient now? Like, come on, right? So so let's discuss this. Why we define P, polynomial time, the way we define it and why we think of it as efficient. Okay? First of all, P is not meant to mean efficient in practice. Okay? It's not, really. So that's the first thing. And the second thing is, what does it mean to be in P? It means that you've done something extraordinarily better than brute force or exhaustive search in some sense. You've done something incredibly smart with the problem. Okay? And this polynomial time is robust to notion of what is an elementary step, what model we use, what kind of reasonable encoding of the input we use, implementation details, right? So are we using a one-tape machine, two-tape machine? Are we considering accessing memory location one step or n steps? How are we encoding the input? Are we using the minimum number of bits, or like are we being more generous? Implementation details, what kind of data structures are we using, so on and so forth. All of these things make a difference. These like things that depends on us, the humans, they make a difference polynomial, but they only make a polynomial difference, right? So in that sense, P is robust under these things. So really, you can think of it this way: being in P is a fundamental property of the problem, rather than property of how we solve the problem. Okay. So P is about the mathematical insight into a problem's structure. It's not about how we solve it, what kind of technology we use, what kind of model we use. It's about the mathematical structure of the problem. Okay, being in exponential time and being in P time tells you a lot about the structure of the problem. So actually, I skipped this, but like, I don't know, whether say theorem proving or satisfiability is in P or not is a mathematical question about the nature of the problem. So for example, you say, okay, I have an algorithm that solves theorem proving in n to the 100th time. So that would be like the best result in computer science history. Not because it shows P equals NP. And not because you would collect like $1 million. So that's not why it would be the best result in CS history. The reason is because you are showing, like we have this problem that we have no idea how to do, and we think it's like a super complex problem. We have no idea how to search the solutions in this space, and you're doing like something extremely, amazingly clever if you're able to find the solution in n to the 100. Okay, so that algorithm would have, I'm sure, amazing applications and insights into it. Even though n to the 100 is not practical in practice, right? Other than this, I would say, well, it has nice closure properties. You know, you plug in a polynomial time algorithm into another polytime algorithm, you get a polytime algorithm. And, you know, you can say, well, you know, P time n to the 100 is like too much. I'm not comfortable having n to the 100 in my definition of efficiency. Well, okay, try to cut it off at some specific exponent. Doesn't make sense to do it. You'll see, like, it just wouldn't work. Like if you said, like, n cubed is my upper limit. Well, why n cubed and not n to the 4? And, you know, if you say, okay, from a practical point of view, we can still make some arguments. We can say, well, big exponents like n to the 100, well, I've never seen it. So they don't really arise. And if you do get like a big exponent like n to the 10 or n to the 20, usually what can be done is that exponent can be brought down to, let's say, n to the 4, n to the 3. Okay. Seems like. So to sum up, being in P versus not being in P is a qualitative difference, not a quantitative one, okay? But like in terms of practical efficiency, you are looking sort of at the quantitative difference. In theory, we are looking at qualitative differences. Okay, so let me now talk about efficiency limits on computation. So we've seen like algorithms can do tricky things and they can be quite powerful. One fundamental question would be like, can every decidable problem be decided in polynomial time? Is every decidable problem in P? Okay, so this is basically what I said. So maybe, yeah, I mean, you could say maybe they can solve, polynomial time algorithms can solve every decidable problem. So this, we can prove that this is not true by argument that's basically a diagonalization argument. Okay, so let me go over this argument. So when we show that halt is undecidable, what did we do? Okay, so this is halt. It takes an encoding of m and x, and it asks, does m halt on input x? We said, okay, let's go by contradiction, and let's suppose that m halt, there's a Turing machine that decides halt. And then we said, okay, let's now take a look at this other Turing machine. I called it m Turing, m sub Turing, that will now use m halt as a subroutine. And what does m Turing do? It's very actually simple. It takes some encoding of a Turing machine. It runs m halt with 2 copies of m, and it, in some sense, flips the answer. Right? What does that mean? So if m halt, m comma m is yes, tells you yes, it halts, then you actually go run for infinity. And if m halt tells you no, you're not halting, then it halts. So in that sense, it's like flipping the answer. And then this leads to a contradiction, because now if you sort of feed m Turing to itself, it gets confused. It's like, should I halt or go infinity? Like, doesn't know what to do. Okay, because we sort of flipped this answer. And you can actually like do a very similar kind of thing for what I want to show right now. So we can use the similar strategy to show that there is a decidable language that takes, let's say, at least n squared time. But there's nothing special about n squared. Like, we can take another time bound if we want. So let's now define this language, HWTB, halt with time bound. So halt with time bound takes an encoding of a Turing machine, runs, and you check if you run the Turing machine on its own encoding, does it take at most n cubed steps? If it does, it's in the language. Okay? And then we say, okay, first of all, this language is decidable. Why? Because given an input, you just run it on its own input, and then you check, does it take n cubed steps or not? But this cannot be decided in n squared steps, the claim is. Okay, so to show that, we're going to go by contradiction. Suppose I can decide in n squared steps, and let MHWTB be a decider with this property. And then we're going to do the same thing. We're going to describe M Turing that uses question.
So I have a question related to HWTB.
Yeah.
Said suppose it does not halt after n cube steps, then
Yeah.
you simply reject it. But what if that's a really large constant factor? So
What
it
if?
does not halt n cube, but it might halt 100 n cube steps.
But I'm looking at like n cube. There's no constant.
So it's not big O of n cube.
No. Yeah. And we'll describe M Turing the same way, basically. So M Turing takes an encoding of M, runs this decider HWTB, and in some sense, again, flips the answer. So how does it do that? So if M of HWTB says yes, which means that it it stops in n cubed steps, well then I'm not going to stop. I'm going to run for infinity. And if it says no, that this takes at least n cubes, more than n cubed steps, then I'm going to immediately halt. And then you say, okay, what happens when we feed M Turing to itself? Again, it's supposed to get confused. Okay, so you say, okay, there are two cases. So it could be the case that MHWTB, M Turing gives you yes, says yes. But if it says yes, it's supposed to mean that M Turing, when it's given its own code as input, should stop in n cubed steps. But what does it do? It goes into an infinite loop. So that's not good. And then you check the other condition. Well, if it says no, which means that M Turing, when it's given its own input, runs for more than n cubed steps, well, what does it really do? So it should take more than n cubed steps, but it actually halts immediately. And if you look at the running time of this M Turing, it's like basically n squared plus c steps. So n squared comes from running the m of HWTB. Right, so our assumption that there was a decider that used n squared steps had to be false. And as I said, nothing special about n squared. Could also consider, say, exponential running time. And if you're a bit more careful about it, you can prove a much stronger statement, actually. Okay, so here's a time hierarchy theorem. You can basically show, the detail is not important, but d time t of n is basically not included, so it's not equal to d time t of n 1 plus epsilon. Okay, so there's some technicality here, Tn time constructible, but doesn't matter. So this is not a theorem like you have to really know exact details about, but there's such a theorem that's like a more stronger theorem. And this shows, for example, that P is not P is a strict subset of exp. Right? They're not the same set. Okay, in the last 1 or 2 minutes, I want to do the following thought experiment. Okay, can you cheat exponential time? So how could you try to cheat exponential time? Well, there are 2 ways that I can think of you can try to cheat it. Well, you can say, let's try to make every step exponentially faster. Let's say I can do a step in like 1 over 2 to the 300 seconds, milliseconds. So what's the problem with that? Because if I can make a step faster and faster, well then, what's the point of talking about running time? I can solve everything efficiently. So the problem here is that as you're trying to make it faster and faster, you have to use more and more energy. In particular, you have to this system is going to probably get really hot really soon, and then you have to really cool it down. So you need a lot of refrigerators to cool the system down. And it turns out if you want to get it exponentially fast, you need exponentially many refrigerators in some sense. Okay, or you can also think of it this way. So I think what's true is that you have to be able to pack in so much energy into this space that something happens and your computer actually becomes a black hole. That's what I hear from physicists. So in some sense, you're trading exponential time with exponential energy. Okay, so the other thing you can try is time travel to the future. You can say, you watch Interstellar, right? So you can say, okay, I'm gonna go on to a spaceship. So I'm gonna set my machine up, Okay, it's going to solve the theorem proving problem. I'm going to hop onto a spaceship, go to like speeds of like close to speed of light, go on for 2 years and come back. Now for me, 2 years in the Earth's time frame was like maybe 1 billion years. Okay, so like the sun is gone, like everything is extinct, but like your machine is still running. And that gives you an answer. Okay, so, well, from my perspective, I solved the problem in 2 years. That would normally supposed to take billions of years. So what's the problem with that? This is, by the way, time travel is possible, right? So the problem here is, again, like you need a lot of energy to take yourself to the speed of light, like to come to close to the speed of light. So if you're not using exponential time, you're going to have to use exponential energy to solve the problem. So there's always an exponential cost. Okay, so seems like there's always exponential cost.